Okay, good day friends. Today we are going to solve this problem, which is a ring made of homogeneous rubber core of length L, mass m, and stiffness k rotates in a horizontal plane around a vertical axis passing through the center of a ring with angular velocity omega. Find the radius r of the rotating ring. So this is really important and really interesting problem because right now we deal with something which rotates but does not just rotate, and you can see it by this thing, stiffness k. So this is really important because right now we work with a core made of a rubber, which is an elastic object which can be deformated, which probably will lead us to work with Hooke's law, because every time when we work with elastic deformations, we apply Hooke's law. Yeah. Okay. So this would be the image of our problem. Yeah. We have two axes which are x and y. Yeah. And at the vertical, this thing is rotated horizontally around a vertical axis. So we have something like this. If you imagine it as a rubber band which is circular and it is rotating, this would be the case. However, as we know, if it deformates as the angular velocity increases, and this thing is going to increase its length because it's going to deformate, and it will not go smaller, it will get bigger because we know that there is a tension force acting on each part of this rubber band. So basically at the very beginning of this problem, we have this object, and what is this thing? It is its form when it gets deformated, when it gets bigger, right? So it is the beginning, and this is the finish, probably. Let's say it like this. But this would be a little bit uncomfortable to work with this kind of picture. That's why let's work with this picture. Yeah, this would be the image from the top, the same thing. However, right now it would be a little bit more convenient for us to work this way. However, let me take even further the situation and work with only with deformated form of this object when it already gets bigger, right? So we can see this thing. This is the L at the very beginning, and at the end, let's call it its total length is got to be something like huge L, and it will totally depend on two things, which are only on one thing, which is the increase of radius, right? So 2 pi is constant and radius is going to change. So this is the thing that we really need, and that is the thing that we really need to find, which is the radius, new radius. Okay, good. Let's get back here. Let's draw this central point, and we know that our band goes around like this, but this is just an extra information. Right now, let's work with static situation. Let's take a small part of this band. It's going to be so small, something like this, let's say. It's going to be so small that we cannot even measure it, let's say. It's really, really small, which is something like a dm. So if the m is the mass of the entire band, something like if the m is the entire L, then dm is just the small dl. So this thing is going to be small dm, the small mass of the entire this chord, and also a small length of this entire chord. Yeah. Right now, let's just take it as a dl, but also its mass is just a small dm. This would be very important. However, if I draw it a little bit bigger, if I zoom it in, it's going to be something like this. Probably let's draw it something like this and like this, because it would be a little bit more comfortable to us to work with something big. Yeah, in fact, it's still that small, but we zoomed in. Okay, so let me tell you one more thing. When we take something very small like this, we can see that this part, in fact, is very smooth. It's just a very straight line. The same thing happens on our Earth. So the Earth is a sphere, something very close to sphere, a form called geoid. However, at the surface, we can see that it's very how can I say it, smooth, yeah, something like flat. However, it's not flat, it just looks flat, but in fact it's still spherical because the radius is so huge. It's about 6,300 kilometers and even more, right? Okay, right now we work with this equation. We still remember that this thing is just a straight line because in the small scale it looks so straight. Okay, and if we have this small part of the rubber band, rubber cord, then we can definitely say that this part of small rubber cord is being pulled by other parts, by other DLs of the rubber, right? And the same thing happens here. It is pulled from both sides. This is really important. And also, let's say that this is angle alpha. Yeah, let's call it just alpha. Okay. And if I take something in half, it would be alpha divided by 2. This would be alpha divided by 2 as well. This would be 90 degrees and 90 degrees. And as we can see here, we see that this thing has two components, vertical and horizontal. The same thing happens here. It has vertical and horizontal components. As we can see this thing, if we again take this idea that this thing, in fact, is very small part of this circular band, then we can see that this vertical axes are, in fact, the forces, yeah, which pull our band inward, yeah, and these horizontal parts are the forces that is pulling our DL to the sides, and that what makes our band stretch, go bigger, right? So let me take this out, Let's call this thing tension force, right? This is tension 1, let's call it tension 2, because we're not sure if those two things are equivalent to each other. However, what we do know is something like this. If this thing is alpha divided by 2, this is 90 degrees, this is 90 degrees as well, because the force acts with normal, right? With it would be perpendicular to our radius. This is radius. We should not forget this thing. Okay, so what we know else is that if this thing is alpha divided by 2, 90 degrees, this thing's going to be 90 minus alpha divided by 2. And the same thing, we can know that this part is just alpha divided by 2 again. Same thing happens in here because it is exactly the same thing. Okay, let me take this off so we do not mess this up. And we can just apply its components with trigonometry. It would be T1 sine alpha divided by 2. Should not forget about that. This is going to be T1 cosine because it's adjacent, right? Same thing happens here to cosine alpha divided by 2. This is T2 cosine sine alpha divided by 2. Okay, good. However, what we do know is that the forces pulling us inward, which are vertical axes, are the same from all the sides. So it does not pull from one side inward stronger than from the other side. So let's say that if it pulls inside this part of the rubber band, it does not mean that this part is getting pulled stronger than this certain part. In fact, they are all attracted into the center with the same force, right? However, horizontally, they might not be equal to each other due to the direction of the rotation. Yeah, because this is really important for horizontal axes. Okay, so that's why it would be just T sine alpha. This thing's going to be just also T sine alpha, not T1, T2. It would be just T sine alpha from both sides, so they are equal to each other. Okay, this is really important to understand. Okay, right now we can work with this thing. Let's write down our basic Newton's second law, which is just sum of forces equal ma. So what forces are pulling us in? It would be 2t sine alpha divided by 2. Why 2? Because we have two of them, this part and this part. That's why we have two of them. We will write here 2t sine alpha divided by 2. Let's get it into the brackets. Also, we have ma, but it's not ordinary ma. As I have told you, if this thing is dl, it has a mass of dm. It is really small part, and this small part has a small mass. That's why we'll write here just a dm a. Yeah, acceleration would be the same because for even the small part or the entire part, it would be the same acceleration, in fact. Okay. However, we don't know many things, right? That's why we need to define all of these things. We need to define tension force. We need to define sine alpha divided by 2. We need to define dm, and we need to define acceleration, because we don't know any of them. And right now, let's try to find what they mean exactly. So first of all, let's start from the easiest one, which is acceleration. And we know that this acceleration is centripetal, not an ordinary. And we know its formula is just v squared divided by r. And also we know that v has a formula which is angular acceleration multiplied radius. And if we put it here, it would be something like omega squared r squared divided by r. We can cancel this out, and we will have something like omega squared r. So this would be the meaning of our angular centripetal acceleration. Yeah, thank you. This would be a very helpful thing. Yep. Good. Okay, what about dm? What is the meaning of dm? dm, as you can see it here, yeah, if we have mass, which is responsible for the entire length of the new length of the band, and we have a small mass, which is responsible for just a small part, it would be something like this. We definitely know that, let me bring it here probably, let's put it something like this, yeah? Yeah, that would be good. We know that the proportionality between these two things would be equal to proportionality between these two things. Yeah, because if the fraction, if the relation between mass to the small mass would be the same as the relation between the entire length and the small length, right? So we can do this kind of thing, which would become m divided by dm equals L divided by dl. Yeah, and we also know that this L, at the very beginning, we have told you that this is 2 pi r. This is really important. Okay. Basic maths, it is going to be something like dm is going to be equal to m multiplied dl divided by l, but instead of l, I will write here 2 pi r. Yeah, this would be the meaning of our dm. Okay, right now we have two things known. What's the meaning of sine alpha divided by 2? So basically, if you look at here, we have this triangle. Let me draw it with green, I don't know, something like this. This triangle, we have this angle, which is alpha divided by 2. And we know that if we have an angle, the sine of this angle would be the relationship between opposite side and hypotenuse. Yeah, and we know that this opposite side would be just the half of this dl. This would be dl divided by 2. Okay, good. And if we know that thing is got to be, yeah, dl divided by 2 is got to be, let me bring it somewhere here, even further. So, yeah, sine alpha divided by 2 would be the relationship between opposite side to hypotenuse. And opposite side, as we have told you, it's this side, dl divided by 2. Let me put it here, dl divided by 2. And hypotenuse would be just our radius, right? So this would be r here, and just the basic maths, it's got to be dl divided by 2r. So this would be the meaning of our sine alpha divided by 2. That's good. Let me highlight it. Yeah. Right now, the last thing that we need to work on is our tension force. And this is very interesting and very tricky one. Tension force is exactly the force which is responsible for our stretch. Yeah, this is the force that makes all of that length increase, right? So that's why our band gets deformated, because each part of the band pulls another part of this band, and that's how it increases. And that's how we implement here Hooke's law, which is F equals K delta X. So we know that F is the force that is responsible for our stretch, K is the stiffness of our material, and delta X is the difference between initial and the final lengths. So the force which is responsible for our stretch is tension force. K is just K, and X final minus X initial would be our final length and the initial length. So it would be something like huge L minus small l. But we know that huge L is 2 pi r, so let me write it like this. Yeah. So that would be the meaning of our tension force, and it's really important part. Okay, right now we have all four. We can write down it in the full form, right? Let me take this thing and copy it again. Probably, I don't know, let's put it somewhere here, I don't know. Yeah, why not? So let's put all them into their places, and we know that 2 is just 2 right here. Let's put it something. Yeah, tension force has got to be this part. Let me take it and copy. It would be here, multiplied our sine alpha divided by 2, which is here, this thing. Then we have here our dm, which is this part. And the last thing, but not least, it's the centripetal acceleration, which is right here. Yeah, good. Okay, right now, let's make some basic calculation. What can we get rid of? So I can get rid of this dl and this dl. Good. What else? I can get rid of this r and this r. I can get rid of this 2 and this 2. And I guess this is the end. Yeah. Okay, if I just open this brackets, it would be just k, let's write it like 2 pi rk. Let me write it like kl. Okay, and at the bottom we have just only radius. Yeah, but I can write it just, if I write it like this would be correct, but if I write it like this would be still correct. Yeah, because it's basically the same meaning, like this thing is just 1 r, is the same thing. However, let me write it like this, so it was a little bit more comfortable for me for calculation. And here we have what? Mass, angular acceleration squared, angular velocity squared, I'm sorry, and 2 pi. Yeah. Okay, so at the top it's just m omega squared divided by 2 pi. Yeah, good. So I can get rid of this r. I can move this thing here, move this thing here. And then I will have something like this. It would be just 2 pi k minus m omega squared divided by 2 pi equals kl divided by r. Okay, good. If I make it a common factor, yeah, if I multiply it by 2 pi, and at the bottom it will be also 2 pi, yeah, it would be something like this. 4 pi squared k minus m omega squared divided by 2 pi equals kl divided by r. And also right now I can make this kind of a thing. Yeah, I can multiply it and change places. It's gotta be just radius equals 2 pi goes to kl, it would be 2 pi kl, and at the bottom I will have 4 pi squared k minus m omega squared. So this would be my final answer for radius, because right now I have all the things, all the factors that I am given. 2 pi is just a constant number, 4 pi squared is also a constant number, k is given, l, small length at the very beginning, is also given, as you can see it here, and mass at the beginning is also given, it's here, and angular velocity is also given, which is here. Yeah, so okay, this would be our final answer. That's why we have finished. Okay, thanks for your attention, and if you have any questions, you can write me privately.